Hello students, this lesson is over, this video is over lesson 68, which is the probability multiplication rule. And this is for my pre-algebra classes. You may want to take a moment and pause the video to copy down what's on the screen, and then go ahead and hit play again, and then you can just listen. So, first of all, in this lesson we encounter what's called the fundamental counting principle. And it says if an experiment has two parts, the first part with m outcomes and the second part with n outcomes, then the total number of possible outcomes is m times n. And so if I grab a dry erase board, if I can actually pick it up here, if we talk about this for just a moment, so if you imagine the front row of my classroom has 6 seats. And I want to figure out between these 6 students, how many different ways could I stick them, fill these 2 seats? So there are 6 students that could possibly sit here. But once I have a student sitting here, how many students could sit there? 5. So how many different ways could I put 2 students sitting in these 2 seats out of the 6? Well, 6 times 5, there are 30 different ways I could arrange these 2 seats. Now this principle can be extended, and we could keep going with the same idea. So if I have 2 students already seated now, how many students could I potentially stick in this one? Well, there are 4 students to choose from. So how many students are there to choose from here? 3. How many to choose from here? 2. And there's only 1 student left over, so he or she has to sit right there no matter what. So actually, if I wanted to find out how many different ways could I arrange this front row of seats with 6 seats and 6 students, well, multiply that all together and you're going to have your answer. So 6 times 5 is 30, times 4 is 120, 360, 270, well, still 270. Or it's going to be 720. I got that backwards. My apologies. 720. So there are 720 ways I could potentially arrange 6 students. The fundamental counting principle is also the reason why you'll see sometimes a restaurant, especially let's say a burger joint, can talk about having over 1,000 different burgers, individual burgers they could make, because they could be talking about the different kinds of bread that they have, the different kinds of meat that they have, the different kinds of cheeses that they have. You could talk about different types of condiments, like do you put ketchup on it? Do you put barbecue sauce on it? Do you want mustard? Do you want mayo? Do you want pickles? And so let's say they've got 6 different types of bread. Let's say when it comes to meat, let's say they've got 5 different kinds of meat that they can make for you. Different types of cheeses, so I mean, if you have 3 different types of cheeses, well, you could actually do just this cheese, or just this cheese, or you could do just that cheese, or you could do these 2 cheeses, or you could do those 2 cheeses, or you could do these 2 cheeses, or you can do all the cheeses together, or you could do no cheese at all. So right there, that's 8 different options. And then ketchup, ketchup is really just a yes or a no. So there's 2 options there. Barbecue is a yes or a no. Mustard's a yes or a no. Mayo's a yes or a no. Pickles is a yes or a no. And I mean, there's so many more options that we can put on there. But if we just stop right there and figure out how many different kinds of burgers, just with these options, could we potentially make? So if we can multiply those together real quick. Give me just a moment. Right there, you would actually have 7,680 different individual burgers you could make. So next time you see a claim like that coming from a restaurant or a burger joint, Don't be too impressed. It's pretty easy to get that number up there quickly because the fundamental counting principle tells us that we can multiply the options of each individual thing to find the total number of options. Now, related to that, let me get rid of my board here. Related to that is the multiplication rule for probability. Now, this comes in two different forms, though. And so it depends on what relationship our events have. And so what we have first is what's called an independent event, independent events. So remember that the prefix in means not. So these are things that are not dependent. Okay? The outcome of one event has no effect on the outcome of other events. Okay? So these guys do not depend on what happens with this event. Okay? So in the case of just two events, if I'm going to do this first and I'm going to do that second, this guy does not depend on what happens with the first one. So some good examples of independent events would be like flipping a coin twice. So if you flip a coin once, and let's say you get heads, does that make it more or less likely that you'll get heads or tails the next time? Does that change anything about the next flip? No. If you get tails the first time, does that change anything about how likely it is to get heads or tails on the second flip? No. So the second flip does not depend at all on whatever you got in the first one. A really easy way to come up with a good list of independent events is to really look for just two things that you can do that have absolutely no connection to each other. So, for example, we can keep our coin, but this time I might just flip it once, and then let's say we spin a spinner. So does flipping that coin affect what I'm going to get on my spinner? Absolutely not. Another thing that we often do is we pull marbles from a bag. So let's say I pull a marble, and then let's say I roll a die. So whatever color marble I pull, will that affect what number I roll on my die? Not at all. Some other things, there are some things that we can just do twice in a row and it has no effect. The first outcome has no effect on the second outcome. For example, if we go back to our spinner, we could spin a spinner twice. What you get on the first spin does not affect what you get on the second spin. For that matter, you can roll two dice. What you get on the first die does not affect what you get on the second die. When it comes to pulling a marble, we got to be a little careful. However, if we pull a marble and then replace it, and pull again, that would be independent. Since we put the first marble back, the bag now has the same number of marbles it had before. So when we pull a second marble, assume we scramble them up a little bit, the first marble will have no effect on the probability of the second one. So this is something that we call, I'm going to fix that up there, a little something that we call replacement. So we pull two marbles from a bag with replacement. Means that before we pull the second one, we put the first one back. So as long as our events are independent, they have no effect on each other, which therefore means that we can simply find the probability of both. So the probability of our first event and our second event happening. And when we say this, there is a certain assumption that this comes first, followed by that. But since they're independent, it really doesn't matter. So what we're going to do to find the combined probability is like the fundamental counting principle, is we're just going to take the probability of the first event and multiply it by the probability of the second event. So at this time, I'd like you to please grab your orange highlighter. So hopefully you already did your yellow up there. Grab your orange highlighter. This is a formula that we're going to go ahead and stick in orange here. And we'll do a few examples of what this should look like. So the probability then of flipping a coin twice and getting heads both times. So if I want to find the probability of getting heads both times, so this is probably getting heads and then heads again. So, ladies and gentlemen, this means, since they're independent, that we're just simply going to find the probability of getting heads the first time, and then we're going to multiply that by the probability of getting heads the second time. Now, I'm not going to make you write that part out, but I do want you to write their probabilities. So what is the probability of getting heads? Well, heads is one option out of two possible, so 1/2. Times, what's the probability of getting heads again? Well, same thing. So therefore, what is the probability of getting double heads, two heads in a row? 1/4. So if we flip a coin twice, about 1 try out of 4, we expect to get double heads, approximately. So for our next example, if we were in class, I would ask you how many of you have ever played the game Settlers of Catan? So in Settlers of Catan, there's several different expansions, and one of the expansions, you end up getting a yellow die and a red die, and they actually do slightly different things. And so let's say that you're playing this game and you realize that on your next turn, if you can get the yellow die to be 1 and you can get the red die to be 6, you win the game. So what's the probability that you win the game on your next turn? So we want find the probability of the yellow die being 1, and then we want to know the probability of the red die then also being 6. Well, what you roll on the yellow die doesn't have any effect on what you get on the red, so these are independent. So this is going to equal then the probability of yellow being 1 times the probability of red being 6. So on the yellow die, what's the probability of getting a 1? Well, a 1 is just one option out of 6 total. And then for the red die, getting a 6, well, 6 is only one option out of 6 total possibilities. So the probability that you're going to win on your very next turn is 1/36. The odds are not great. It could happen, but I wouldn't count on it. And finally, let's take a look at a spinner. So we're going to make our spinner here. And my spinner, I'm going to cut it in half right there. And I'm going to cut just the top portion in half. And let's say we have a section A, section B, and section C. And so here, I want to know what is the probability of spinning an A and a C. So probability of spinning an A followed by a C. Well, since one spin has no effect on the next spin, these are independent. So this is the probability of A times the probability of C. Well, the probability of A, when we look at this, this is a geometric probability, so we think a little geometry. So how much of the area of the circle is A taking up? Well, A is taking up 1/4 of the circle times how much of the area is C taking up? Well, C is taking up half of the circle. So therefore, the probability of spinning an A followed by a C is 1/8. So now let's flip to the back. And you might want to pause just for a second and get that copied. So we've looked at independent events where they do not, you remember in means not, they do not depend on each other. So dependent events, the outcome of one event has an effect, or it depends on the outcome of the other events. Okay. So the outcome of one event has an effect on the outcome of the other events. So the other events depend on what happens with this one. So an example of that, which we've already kind of alluded to, is if we pull 2 marbles without replacement. If I don't put my first marble back, then there's not going to be the same number of marbles in, which means it's not going to be the same probability for pulling another marble as it was for the first. Another very simple one, sometimes we do look at probabilities in math talking about decks of cards. So also if we pull 2 cards from a deck without replacement. Oops. We could also apply this to the classroom. So if I had to choose a couple students to go help with something, and so what would be the probability that I would choose, let's say, 2 girls? Well, if you take a look at the probability of me choosing the first girl, if I were just randomly pull a name out of a hat, there'd be a certain probability there. But the moment I've chosen that girl, I'm not going to choose her again. I'm not going to put her name back in, which means now the probabilities have changed. So if there were a total of, let's say, 20 students in the class, then all of the probability of the girls would be something out of 20. The probability of the boys would be something out of 20. But if I don't put that one name back, now they're all going to be probabilities out of 19. So when we have this, our property, our formula changes. So the probability of A and B. So remember, there's an assumption here that this is happening first, followed by this. So we could almost say the probability of A, then B. Well, this is going to be simple for the first part, because the probability of A, that's the first thing happening, so it's just your plain simple probability like it always has been. However, because B is going to change, the way we write this for dependent events is we say the probability of B, but we can't just write the probability of B because it's no longer the same as what it was before. So the way we represent that is we say the probability of B given A. The probability of B given A. And so this B given A part here just means what is the probability of B happening given that A has already happened. Oops, forgot an E there. Happened. There we go. So what is the probability of B happening, given that A has already happened. So for this, let's take a look at our bag of marbles. And if you didn't know we had a bag of marbles, well, now you do. So there's the top of my bag. It's my bag comes down here. And inside my bag, I've got a bunch of marbles. Specifically, I have 2 white marbles, 1 blue marble, and 3 red marbles. So I want to find the probability of pulling out 2 red marbles. So this is going to be the probability of pulling that first red marble. But then times the probability of pulling a second red marble, given that I've already pulled a red marble out. So the probability that I'm going to pull a red marble, well, there are 3 red marbles out of, well, 2 plus 1 plus 3 is 6 total. The probability of R given R, though, so if I've pulled a red one out already, there are no longer 3. We've pulled one out, so there's only 2 red marbles left. So what's the probability of pulling another red? Well, now there'd only be 2 red marbles left. And since there's only 2 of those, plus 1 plus 2 is out of 5 total. So this actually would be a 1/2, 3/6 is 1/2, times 2/5. Little reducing before multiplying. Both of those become 1s. And we can see here the probability then of pulling 2 red marbles is 1/5. So about 1/5 of the time you would pull 2 red marbles. So let's see what would happen if I want to know the probability of pulling 2 white marbles. So likewise, this would be the probability of pulling the first one. The first one's just easy, it's just normal. So there are 2, let's stick with red, sorry, 2 white marbles out of 6 total. But then we're going to find the probability of pulling a white marble, given we've already pulled a white marble. Well, if we've already pulled a white marble, now there are only one white marble left, and then 1 plus 1 plus 3 would be out of 5 that are in their total. So this would then be 2/6 is 1/3, and then this is 1/5. So probability is 1/15. So if I'm pulling 2 marbles out of a bag without replacing them, then about 1/15 of the time I'm going to pull 2 white marbles. Let's go ahead and find the probability of pulling 2 blues. So the probability of 2 blues, we're going to start with the probability of pulling the first blue. So the probability of pulling the first blue, well, that's 1 blue marble out of 6 total, times what's the probability of pulling a second blue marble, given we've already pulled a blue out. Well, if I've already pulled a blue out, well, then there are no more blue marbles left. So can you pull another? Well, obviously not, which means that this is impossible. And if this is impossible, it has a probability of 0, which means if it is impossible to pull 2 blue marbles, the probability is 0. Let's switch over to a deck of cards here for one last example. We'll skip a couple lines. And let's say we want the probability of pulling a king followed by another king. So I want to pull 2 kings out of the deck of cards. So for those of you who are unfamiliar with the deck of cards, play a little more solitaire. but in the meantime, we'll help you out. So in a deck of cards, remember there are 4 suits: hearts, diamonds, spades, and clubs. And then in each suit, there's kind of a 1 through 10, except for we don't have a 1, there's an ace. So ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you get a jack, a queen, and a king. So that's a total of 13 cards in each suit. 4 suits, 13 cards in each suit. So that means that I need to find the probability of pulling this first king. Well, there are going to be 4 kings in the deck. King of hearts, king of diamonds, king of spades, and king of clubs. Out of a total of 4 times 13, 52 cards. 52 cards on a deck. Times the probability of pulling a king, given that I've already pulled a king. Well, if there were 4 before, now there are only 3. And if there were 52 cards total before, well, now there's only 51. So 4 over 52 really is 1/13 times, and then 3 over 51, if you know that, is actually 1/17. So this is 1/13 times 1/17, which then has a combined probability of 1/221st. So if you're pulling 2 cards out of a deck, you can expect to get 2 kings about 1 time out of every 221 tries. Not very likely. Could happen, just not very likely. And that, ladies and gentlemen, is the end of lesson 68.